Okay, hello guys, welcome back to my channel Gamma Die Gamma. So in this video, let's talk about some coordinate systems, because in the past videos, I've at least the one video on differential operators, I talked about the polar coordinate system or a spherical coordinate system. I didn't really talk about what they mean, what the basics are, what the ideas behind them are. So in this video I would like to give you a brief, if not complete overview of at least the important coordinate systems, which includes the cylindrical, spherical, and the polar coordinate system, which is a special case of the cylindrical system. Okay, so let's get started. Okay, any discussion of coordinate systems has to begin with the description of the position vector. So position vector, and permit me to be a little more geometric with the explanation, and it is kind of fitting because we've been looking at vectors as sort of arrows whose lengths denote their magnitudes and their angle with respect to the horizontal axis denotes their specific direction. So take a point P and say you have the origin here. And we're working in R3, so origin is 0, 0, 0. So the position vector is a vector that originates at the origin and terminates at the specific point. So this is the position vector of point P. And since we use this kind of representation, the position vector pointing at point P is the magnitude of that is basically the distance of point P from the defined origin. So you need to be clear what the origin is. Okay, so in the Cartesian system, the position vector can be represented as some R1 component, E1 hat, plus R2 component, E2 hat, plus R3, E3 hat, which you, using subscript summation, you can write as Ri E sub I hat. And only in the Cartesian system, in the regular coordinate Cartesian coordinate system, are the Ri's equal to the Xi's. So this is just Xi E sub I hat, which makes R vector, you can write R vector, the position vector, at some point say X, Y, Z from the origin as X E1 hat plus Y E2 hat plus Z E3 hat. And if you sort of consider this as your vector field and you sort of graph it out, assuming this is your origin, all these position vectors are basically radially pointing outwards. Again, with varying magnitudes as X, Y, and Z increase, so does the magnitude of these vectors. So this is for the position vector in the case of the Cartesian system. And you clearly notice, if you take the magnitude of this guy, you clearly get the square root of x squared plus y squared plus z squared under a square root. So, and this is clearly our definition of a distance in a Euclidean space. So this idea of having the magnitude of the position vector denoting the distance of the given point from the origin clearly makes sense, because our point in this general case was just x, y, z. And now the magnitude may not be defined this way. For example, if you take a hyperbolic space, it's pretty different. You have a negative sign inside the square root, and things are not what they are in a nice Euclidean space. But this is the basic idea of a position vector, and we are going to use the position vector for defining new coordinate systems and basis vectors of those coordinate systems. Okay, so let's move on to a cylindrical system. A cylindrical system is a system where you have defined so instead of like x, y, z, which was your Cartesian system, you now have the free variables rho, phi, and z, such that your x in your Cartesian system is nothing but rho times cosine of phi, y is nothing but rho times the sine of phi, and z is just z. So there's no change in the z. And how do we define these quantities? So assuming you have your xy plane here, so assume this is like a circle, you're just seeing it from some other view. This is x and this is y. So define this as your angle phi, and assuming you see the boundary of this sort of circle, assume that length from the origin to that boundary to be rho. Is usually the distance of that point from the origin, that's rho, and z is just like in your Cartesian system, it's the length or how high up you are on the z-axis. So the way to invert them is to see that rho is, since it's just the distance on the xy plane from the origin to that given point, is the norm on the xy plane, which is x squared plus y squared square root. Phi is the angle that this guy on the xy plane subtends with the x-axis. So that will be just the inverse tangent of y over x. Using trigonometry, you can see that makes sense. And z is just z because nothing really changed with that guy. This is your cylindrical coordinate system, and you may notice that it's called cylindrical because if you say that your rho is a constant and you let phi rotate from 0 to 2 pi, and you clearly define some range for your z, say I don't know, -2 to 2. This entire construction traces out a cylinder from z is equal to -2 to z is equal to 2, having a constant radius, I don't know, call this k or something. So this radius is k. So that's why this is called the cylindrical system. And it in many cases in physics, in math, when some integrals, some equations are hard to solve in the Cartesian or any other coordinate system, it may be convenient to write them in the cylindrical system, because that may help us, that may actually save us a lot of trouble. Another thing I want to point out is that this order of rho, phi, and z, you need to maintain that because this is what keeps our coordinate system right-handed. So such that if you have a basis vector, say e rho hat and e phi hat, if you cross them up, you get ez hat. You don't get negative of that. So there's this like order, just like x, y, z had an order, and the order wasn't y, x, z. It's the same way. You have to keep this. You have to obey this order. And again, all the coordinate systems we'll be talking about are going to be orthonormal. So if you dot any of these guys with each other, say e rho dot, this will be 0, but if you have say e rho dot e rho, this will be 1. Another special thing I would like to point out, and which wasn't the case in Cartesian coordinate systems, was the basis vectors are point specific. So let me just write that down. So we have point specific basis vectors. So that means if you have, say, this is your origin here, and this is, say, your point P. So your e rho hat will be radially pointing outwards at that point. So assume this is e rho hat. Ez hat is like before. This is in the z direction, and e phi hat is sort of orthogonal to these guys. It's in the direction where phi increases. So if you vary phi and take like the difference between those two phi values, and you make that difference really small, that's the direction in which e phi hat points. So I hope you can visualize it sort of into the page here. I couldn't really draw into the page, but it's sort of into the page here. But this is just for point P. If you had, say, another point, I know V over here, then your e rho hat would be just radially outwards. So this is e rho hat, for example. Ez hat is again as before. One thing you can rely on is the invariance of ez hat, because it's just the same as the Cartesian ez hat. And e phi hat is again sort of here. So it's hard to visualize, but they're sort of mutually orthogonal to each other. This was for another random point V. So you see that these basis vectors, the directions of these basis vectors are really point specific. They depend from point to point. So this is going to be a challenge when we actually define these guys. The position vector can be defined as, say, if you already established what your basis vectors are gonna be, say e rho hat, e phi hat, and ez hat. You can define the position vector in this new coordinate system, in this new cylindrical system, by dotting the original position vector, expressed in Cartesian coordinates, with the basis vector, and then multiplied with the basis vector, plus projection of the position vector on the phi basis vector, and do the same for the ez hat basis vector. So this is what this looks like, and you can write this as r sub rho e sub rho hat plus r sub phi e sub phi hat plus r sub z e sub z hat. So assuming you have some vector b, just say at point P here, and this is your origin somewhere here. So you at point P you locally define this coordinate system. So the radial direction, this is going to be your e rho hat. Ez hat again is sort of in the z hat direction. Your e phi hat. So if you want to write a vector b in terms of components, express B in terms of in this cylindrical system. So we need to find components for each of these guys. So we want to find a rho component, a z component, and a phi component. So the way you do that is you basically dot B with this and you get some length value that is going to be your phi component. For the z, you again dot it with the z. You get some fixed length value that will be your z component. And for the phi, you again dot it with the phi basis vector. You get the phi component for the vector b in the new coordinate system. So that's how you express b in the new system. Okay, and of course you can use subscript summation for this, and I will cover that like soon when I discuss the general curvilinear system. Okay, moving on to the next one. Okay, so the next coordinate system, which is really useful, is the spherical system, in which case x, y, z, instead of having free variables x, y, z, you now have free variables rho, theta, and phi. And again, maintain this order because this is the right-handed way. And again, which means, and I will cover pseudo objects soon, where we will discuss about this idea in depth. But what this actually means is that if you define basis vectors for this system, and again, all the systems we will discuss are orthonormal. E rho hat crossed with E theta hat is equal to E phi hat and not negative E phi hat. Same thing with E theta hat dot crossed with E phi hat will give you E rho hat. So they're in this cyclical order. So keep this order. It's not rho phi theta, rho theta phi. And again, the conversion goes like this. X, your Cartesian coordinate, is rho times sine theta times cosine of phi. Y is rho sine theta sine of phi. Z is rho times cosine of theta. And again, the inverse of these guys is rho is equal to square root of x squared plus y squared plus z squared. Your phi, you can invert this as cosine inverse of x over x squared plus y squared. But I don't really prefer this. I prefer the inverse tangent of y over x because this is just like our cylindrical coordinate system and it's easier to remember. Theta is cosine inverse of z over square root of x squared plus y squared plus z squared. So this is the inverse conversion between these guys. Let me define what these guys really are. Assuming you have a sphere, because again this is a spherical coordinate system, the best way to actually visualize what these guys are is to see, assuming you have some point here, say P, define this vector, this position vector. So this distance between point P and the origin is what defines your rho. For phi is like before, it's the distance, it's your angle that say this point subtends on the xy plane. So you need to project. So if you have this point, say like this, you need to project this on the xy plane. So let's say this is your sort of your x-axis. So phi is like that angle that the projection of P on the xy plane makes with the x-axis, while your Again, this I said this length is rho. Your angle theta is actually your angle that you subtend from the z-axis. So from the z-axis, say this angle. You don't need to project it, just that angle is your theta. So if you draw a better picture and you actually do some geometry, you'll notice that you can derive these quantities easily using this idea of or the definition of what these guys actually are. So I hope this drawing wasn't too shabby for you guys. So this is what this spherical coordinate looks like. And again, if you keep your rho constant, say is equal to k, you let your theta basically go from 0 to pi, and your phi go from 0 to 2 pi, then this will trace out a sphere with radius k, centered at the origin, of course. So that's why this is called the spherical coordinate system. It clearly makes sense. You can define your position vector just like we propose to do for our spherical or cylindrical system. Just take the projection of the position vector in those basis vector directions, and you get those respective components. And again, just like before, just like our friend the cylindrical coordinate system, even these guys are pretty much point specific. So the basis vectors are point specific. So if this is your origin, if this is your point P, again the radially pointing vector is your rho hat, the vector that points in the sort of the changing phi direction. In this case, it's sort of going into the page. It's kind of hard to draw. And your theta is sort of in the other direction, in the direction of like the changing theta. It's not really down, but it's really hard to visualize. So if so rho hat, e rho hat is in the changing rho direction. Phi hat is like in the changing phi direction. At that point, it's, as I said, it's point specific. And then this guy will be, I think, sort of like this, the theta hat, in the direction of the changing theta. And if you sort of do the this cross product between them, you kind of notice that they're following a certain trend here. It's really right-handed, at least the way I've drawn them here. If you can check, you can do your right hand rule, you can check. They're really right-handed coordinate systems. So this is again point specific. If you have a vector, say B, that is, say, I don't know, rooted at point A, draw the basis vectors at point A. And then dot vector B with all this. So take the projections basically, and you'll get the components of B in this spherical system. The way I've drawn it, unfortunately, just tells me that B is purely in the e rho hat direction. So in this case, it will just be this, because B is entirely in the rho hat direction. So again, this is point specific, so if you define another point Q, it's going to be different. E rho hat is radially outwards. Phi hat is sort of in the changing phi direction. Theta hat is sort of in the changing theta direction. The way in the direction that theta increases the most. So there's this idea of like change, and this idea of change will come in handy when we define a general coordinate system, basis vector for a general curvilinear system. Okay, moving on. Now let's consider a general curvilinear system which is orthonormal, because we want any two basis vectors, if they're not the same, to be equal to 0 and to be equal to 1 if they're the same. So assuming you have free variables, say q1, q2, q3, we can define respective basis vectors q1 hat, q2 hat, and q3 hat. And since they're orthonormal, if I represent them with like qi hat with subscript summation, I want qi hat dot qj hat to be equal to canonical delta ij. I want this condition. That's why, otherwise we wouldn't get a canonical delta if they weren't orthonormal. So again, as I said, in the most general case they are point specific. So P, whose coordinates can be denoted by q1, q2, q3, basis vectors at this point are going to be sort of, I don't know, let's just draw them in arbitrary directions, but mutually orthogonal because of this. So let's say, assuming this is q1 hat, assume this is q2 hat, and then assume this is like q3 hat, and of course assume they're mutually orthogonal. So as I said, they're point specific basis vectors at point P. At point P, which is given by say q1, q2, q3 in the new generalized orthogonal curvilinear system. Again, now since we are being a lot more general, the conversion between your Cartesian and your general system, you can't really give like one set of equations for that. So just denote it as x sub I expressed in terms of q1, q2, and q3, and the inverse of this is say qi, where you express that in terms of x1, x2, and x3, the Cartesian variables. And since I kept stressing on this idea of locality and basis vectors changing from point to point, and the basis vectors pointing in the direction of where the variable changed positively, had a positive change. Given all these observations, so let me just write these observations down. First is we're being point specific. So they're changed from point to point, so they're invariant in space. And observation number 2 is point in direction of positive change of the respective variable. So say for example q1 hat will point in the direction where q1 undergoes a positive change. Given these observations, we define qi hat, a general basis vector of this curvilinear system, as the partial derivative of the position vector expressed in terms of q1, q2, and q3 with respect to that variable qi, but multiplied, or rather divided by this scaling factor hi, and this scaling factor hi is nothing more than our attempt of normalizing, because we want an orthonormal system. So this is for normalizing everything. We want that Kronecker delta to just have no other factor associated with. There's no other factor of 5, 6, or for example, because we've normalized it. And again, this is point specific, so this is at point, say, q1, q2, q3. And the way you define your scaling factors, again, since it's a normalizing factor, it's just the magnitude of this guy, because a vector upon its magnitude is just a normal vector in that direction. So assuming you define your a position vector as, say, xj, q1, q2, q3, ej hat. So this is your position vector in the Cartesian system, because we have these Cartesian basis vectors, but each component x, y, and z is expressed in terms of these new variables of the curvilinear system. Only when you have your components expressed in terms, say, if you're converting from Cartesian to a curvilinear, if your Cartesian components are expressed in terms of the curvilinear, then you can use the formula that I've given in basically the star. So this formula that I'm going to star. So assuming you're working in the cylindrical system, you want to express your position vector, which is generally given as, say, x1 ex hat, say e1 hat, x2 e2 hat, x3 e3 hat, in terms of, say, x1. So your x is rho cosine theta, rho sine theta, and z. So only when you express your position vector like this can you use this formula in the asterisk. So assuming we did that, then we can find the basis vector. So take this guy, partial position vector with respect to, say, qi. This becomes partial qj expressed in terms of the q1, q2, q3 as discussed above, with respect to, differentiated with respect to this qi, and we have these basis vectors, Cartesian basis vectors, intact because they're invariant, they're space invariant. And don't forget your scaling factor, you have to divide by them the magnitude of this guy, which is just going to be square root of, say, partial xi with respect to qi squared. Remember this subscript I, that's why you have to differentiate with qi while you change the top part. So this is, you have x1, this will be x2, qi hat again because this was hi, qi hat again with x3 on top, and the square root of this guy is your scaling factor. So you find this, what this derivative is, and then you divide it by the scaling factor, just like our formula told us to do. And that's how you generate your, say, basis vector. Say qi will just be this partial derivative calculation multiplied with 1 over the scaling factor. Partial derivative of your position vector, you can use your chain rule to write this is like this, dqi. This is just chain rule in multivariable calculus. But notice what this guy is. This is just you can write this as divide by your scaling factor, multiply by your scaling factor, because this is like multiplying by 1, which is acceptable. Now this guy in the bracket is just your qi hat. This is your h1 dqi. So this is your relationship between so this is how you represent your infinitesimal change or your infinitesimal position vector in terms of your generalized curvilinear system. Because in the Cartesian system, this is simple. This is just say dxi ei hat. The scaling factor, if you want to think about it that way, is 1, because if you do the partial derivative, this is just 1, 0, 0 for each of the I is equal to 1, 2 and 3 for the Cartesian system. So scaling factor is 1 for the Cartesian system. So you see this formula in the asterisk clearly makes sense. We did a sanity check with the Cartesian system. It clearly works for the Cartesian system. So it definitely makes sense. So this is how you convert between these two guys. And since a vector is like an invariant quantity that does not depend on the system it is defined on, the coordinate system is defined on, both of these guys have to be equal, because both of them are equal to dr hat, infinitesimal change in the position vector. And you guessed it, why is this important? Because this will be important when we actually try to evaluate line integrals and stuff, because we need the dr vector for that. Clearly, that's the definition of the line integral. And that is a discussion for another video. So I hope you enjoyed. I hope you learned a lot. This might have been a little hard to take in. If you couldn't visualize because of my bad drawing, you can look it up online or watch some animation. That's the best way of learning. So yeah, that's it. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Di Gamma. And in the meantime, stay home, stay safe, and peace out. Stay tuned for more content.